Hi, and welcome to our C Applications Lab background. This topic is going to be a little bit different than our previous ones. The reason being, in our previous topics, we added on new C programming techniques. So we learned about variables, we learned about decision making with the if statements and looping. We then expanded into functions, so we know how to compartmentalize our code into very efficient structures. Today we want to highlight what that means as it's related to interfacing with real physical hardware systems. And so we're going to start out by defining digital electronics. They're sort of the communication between us writing code and real applications that are interacting with things like motors and lights and screens. Digital electronics translate our code into those applications. In order to communicate with or through digital electronics, we have to understand their language, which is the language of ones and zeros, or binary. So we're going to introduce number systems today. The binary, decimal, and hexadecimal being the most frequently used. We'll highlight octal as well because it's highly related. Then we'll talk a bit about working with those number systems mathematically, because there are some unique factors to that. Finally, we will end up highlighting some other useful number codes, such as how do we relate numbers to letters and characters that we like to use when we write words and text from the keyboard. So what is the standard for translation between keyboard letters, for example, and numerical codes in ones and zeros? We'll talk about what that is as well. So we're going to have a rounded idea after this background of how the code that we're writing can interact with physical systems. So to start out, we need to talk about analog versus digital electronics. Some of you may already be familiar with this distinction, but analog electronics imply that it is a continuous signal or a continuous voltage waveform over time. So every increment of time has some value of voltage. There are an infinite number of kind of segments you could divide that analog waveform up into, and there are an infinite number of levels represented in this waveform. So smooth, continuous changes are what you see in analog. In digital, you have discrete levels that a voltage over time can be conveyed in. So for us, we talk about on and off. There are systems that deal with more than just two states, but on and off is most common used for this type of communication. So this would be like an analog watch versus a digital watch, right? With an analog watch, you can watch the seconds hand go around and around. Where on digital, you just see it increment as it hits each step. Each minute goes up, each hour goes up. And so those are a digital way of conveying information. To go back and forth between the two, we have to sample or take the value of that analog voltage level at increments of time. Every so long, take another digital sample, and then just keep those as a large array of values, and then maybe translate them back at some point. In fact, translating between the two is a pretty important area of electronics that you'll dive into in some other courses. But every analog value has some digital equivalent in ones and zeros, which is a binary number. And we'll talk more about that in just a moment. But the conversion between analog and digital happens all the time, especially because of how much technology, digital-based technology, we use. But most of the world we live in is actually analog. When we talk, things like wind speed or the speed that your car is moving, the waves moving through the air that carry your voice, the temperature outside, these are all analog qualities. The intensity of the sun, these are all analog qualities, and so they have an infinite kind of resolution and range based on just their actual physical properties. To interact with a digital system, we have to convert that analog to digital, which is what we have. For example, if we record audio to a CD, that's an analog to digital conversion because this is a digital format. And then we can manipulate, move that around our computer, email it to our friend, whatever that may be. Then to play audio back out of a speaker, it has to go from digital to analog again. So we have this D to A, or digital to analog conversion, where we amplify it and then play it. So the physical world and environmental factors tend to be analog, generally speaking, while computers need digital. And so working with digital values is particularly important when we write code so that we understand what our code is doing when it's translated by a computer to a very specific level. And we'll get there in just a moment, but another note about analog is a bit more, it responds a bit more to noise in the signal. So you can hear fluctuations in my voice if something goes by in front of me. You can hear that fluctuation. Whereas in a digital system, a bit of noise won't really matter. It'll still be interpreted as a 0, or it's still interpreted as a 1. So digital systems are much more resistant to noise. And that makes them ideal for rugged environments, such as maybe in your car tire, where a digital sensor is taking the reading for the pressure in your car for a lot of newer types of cars. Your phone is loaded with tons of sensors, so that's how it knows when you turn the screen, where you are with the GPS, how fast you're shaking it with the accelerometer. Houses are more and more having smart features, as well as computers are full of digital logic for all the interactions between the keyboard and the mouse and the peripherals. It's all based on digital logic. So being able to understand and then interact with numbers gives us the power with our C programming to interact with digital circuitry. So at the fundamental level, we have a way of representing ones and zeros with circuitry, and there's a line of mathematics called Boolean algebra that allows you to perform math operations with ones and zeros. So we have electronics that can do math and make decisions, and we have C programming. What we're looking at this week is the connection between what we write in C programming and working with numbers that a circuit can use to drive a motor, to take a value for the pressure in a tire, so on and so forth. So the number systems discussion today is directly based on how does what we're doing in C relate to physical hardware that would create action in the world. And this is relevant to automated manufacturing, as well as smart cars and automated systems and cell phones, anything that has sensor-based decision making. So let's think about number systems first of all. What do we already use? We use a decimal number system which has a base of 10. We have 10 fingers, 10 toes, generally speaking, which kind of makes counting in tens a lot more natural for us. But we use tens for our decimal digits. For example, if you have the number 325, it's really, as written on the page, it's a 3, it's a 2, and it's a 5. But we know because of their order, the 3 means 300, which is 2 squared. The 2 means 20, which is 2 to the first power. And the 5 means 5, which is 10 squared, 10 to the first power, or 10 to the 0 power. So each number, starting on the right, has the weight of 10 to the spot that it's in starting at 0. So 10 to the 0 is here, 10 to the first is here, 10 to the second is here, and so forth for thousands and onward. So these are called the weighing factors. Each digit has a weight based on the number system. So in the number system, our powers of 10 are the weighing factors. So 10 to the 0, 10 to the 1, 10 to the 2, and so forth. So that's how we interpret mathematically 325. It's 5 times 10 to the 0 plus 2 times 10 to the first plus 3 times 10 to the second, and so forth if it was a bigger number. But what if the base was not 10? Instead of based on having 0 through 9 digits, which is 10 total digits, what if we only had two options, 0 or 1? And that is what we have circuitry created to do. It's either on or off. And so a new number system had to be explored that relates this 0 and 1 or on and off logic and connects it back to our decimal number system that we understand. So binary is the name of the number system with only on or off, or 0 or 1 values. Instead of base 10, it's just base 2, so 0 or 1. And the weights of the numbers change because of that. It's not powers of 10 now, it's powers of 2. So the first digit has a weight of 2 to the 0 in decimal, a weight of 2 to the first, a weight of 2 squared, and so forth. So this number line informs us what the weight of these digits are in binary. And that weight allows us to assign the term most significant bit is the one on the very left because it has the most weight to it. So this is our most significant bit of binary. And this is our least significant bit. One other thing I'll mention, in computation terms, each digit is referred to as a bit in binary, B-I-T, a bit. So this is an 8-bit number with the most significant bit over on the left, least significant bit over here on the right. So how do we get from binary, which is a language of ones and zeros, to decimal? Well, we can use this number line and the known weights to do that. So say you have this 8-digit binary number. You would line it up in your number line according to the weights, aligned to the right-hand side, and then just add up the weighing factors. So 1, I'll start on the left. 1 times 128, 0 times 64, 1 times 32, 0 times 16, 1 times 8, 0 times 4, 1 times 2, 0 times 1. Note that the top number is your binary number. The bottom number is just the weighing factor. But you just, everywhere with a 1, you add up those weights, and so 10, 10, 10, 10 in binary has an equivalent of 170 decimal. The subscript 10 indicates that's a decimal number. So it's important when we're working in number systems to mark our numbers with a subscript so that we can know what those numbers are. So we had a 2, we had a 10, for example. So let's look at just another couple examples just to make sure we're on the same page here. So let's say we had 1010. What is the decimal equivalent of that? And to figure that out, we just line up our number line from the previous slide, put the weights in here, which are 1, 2, 4, 8 for the first 4, and we just multiply straight down. What has the 1? So 8 plus 2 equals 10, base 10. So in a binary decimal conversion, 1010 binary equals 10 in decimal. Here's another example. If we have 1, 1, 0, 0, 0, 0, 1, 1. We can again just align that to our number line, and I won't draw the whole number line. I'll just put in some key points here. It's 1, 2, 4, 8, 16, 32, 64, 128. So we just need to add up the weights that are represented here. So 128 plus 64 plus 2 plus 1, which is an equivalent of 195 decimal. So I will note that there are many examples online if you want to see more more calculations like this, you can find that online. And so just look into that. You can find far more videos and examples if you want to see more of this. So going decimal to binary, we have to use those weights and subtract them from the decimal number to find out what the binary is. And so the procedure that I like to use, there are some various setups for this. If you search online for decimal to binary, you'll see a number of different methods. I like the columns. You write your decimal number in the top right. You have your number line in a column along the left. And basically you say, is your decimal number larger than the next number down? And if it is, put a 1 in this column. So 149 was our starting decimal number. Is it larger than 128? Yes. So I write a 1, and then I subtract the weight out of the decimal number. So 149 minus 128 gives you 21. And then I continue this process. Is 21 greater than 64? No. And if it's not, you don't subtract anything and just pull it straight down. So we'll say no. Is 21 greater than 32? No. Is 20, and just continue to pull this down. I'm not drawing ones here, I'm drawing an arrow down. Is 21 greater than 16? Yes. And then 21 minus 16 leaves us with 5. And you can see it on this side as well. Is 5 greater than 8? No. Is 5 greater than 4? No. Is 5 greater, or sorry, 5 is greater than 4. That's supposed to be a 1. And then there's 1 left after that. And then is 1 greater than 2? No. Is 1 greater than 1? Greater than or equivalent for this last line is yes. So you must end up with 0 by the bottom right. So you just take your original number. Is the original number larger than the weight? Yes or no? Answer that question and then subtract. Is it larger than that number? Yes or no? Answer that question and subtract. And then the number you're left with in the middle is your binary number. So 1001, 0101, the example we just did. 149 in decimal is that in binary. So that conversion, just kind of zigzagging down this column, seemingly takes a long time, and we're expanding it out for the purposes of demonstration here, but the more of these you do, the more that it speeds up. So we'll look at one more example here, just to get the idea. We'll look at converting 137 decimal into binary. So if we look at 137, we just need to compare against the weights. So 128, is 137 bigger than 128? Yes. And we are left with a remainder of 9 after we perform that subtraction. So then we're going to have 64 is not greater than 64. 9 is not greater than 64. 9 is not greater than 32. 9 is not greater than 16. 9 is greater than 8. So that 9 comes all the way down here, but then we subtract 8. And then 4, is 1 greater than 4? No. Is 1 greater than 2? No. Is 1 greater than or equal to 1? Would be yes. And so we subtract that last one off. And so the number 137 in decimal is equal to, I'm just looking at the center column here, 1000 1001 in binary. And you just do that by seeing which of these weighing factors fit into your decimal number, starting with the largest. Please, if you have any concern here, explore other examples available online freely all over the place. It is very important that you are comfortable with the conversion back and forth. So the next thing we want to talk about is, what if the base instead of 10 or 2 was 16, and we arrive at a totally new number line? We have 1, we have 16, we have 256, and so forth. But for decimal, so to show 10 decimals, we had 10 decimal digits, we had 0 through 9. For 2 decimal digits, or binary, we had 0 and 1. For hexadecimal, base 16, we need 16 different digits. So we can use 0 through 9, but then to get up to 16 total, we use A through F. And you can see those equivalents here. For decimal, hexadecimal, and binary. So for example, 15 in hexadecimal is F. In binary, it's 1111. In decimal, it's the number 15. We will come back to that in just a moment. But really, we can just think about the base 16 and how that applies. So for example, if I had the number AB in base 16 hexadecimal and I wanted to have that in base 10, I just place it on its number line. So 16 to the 0 is 1, 16 to the 1 is 16. So we have A, B. We know A is represented, that represents decimal 10. So what this is going to mean is the decimal equivalent is 10 times 16 plus B times 1, which is 11 times 1, or 171 decimal. So the weighing factors allow us to translate back to decimal from hexadecimal. We also are not really going to talk about octal. You won't use this that much, but it may kind of rarely come up. Octal is if you have a base of 8, so the conversions, identical conversions apply here. One more example I'd like to do before we move on is just looking at decimal to hex. You can use the same technique. For example, if you want to go from 38 in decimal to hex, how would we do that? Well, we just use the same number line subtraction that we did with binary, but we just have to use the powers of 16. So first of all, 16, you have to know the powers of 16. So 16 to the 0 is 1. 16 to the first is 16. 16 squared is 256. So there's your number line. Does 38 go into 256? No. Does 16 go into 38? Yes. The option here is more than just yes or no, though. It goes, how many times does 16 go into that number? And it goes 2 times. And then what's remaining after you take out 16 times 2 is just a 6. And then does 1 go into 6? Yes, 6 times. So 38 in base 10 equals 26 in base 16. So be very careful. Watch the subscripts. They indicate what the weights of the digits are. Again, please make sure you think about and kind of comprehend fully moving back and forth between these number systems, because it's a very important concept. One thing we want to note are some relationships between these numbers. Binary and hexadecimal are both powers of 2. They have the base of 2, and hexadecimal the base of 16. They have that base of 2 relationship in that every 4 binary digits represents 1 hexadecimal digit. So for every 16. So 4 ones give you F, 4 zeros give you 0. It maps directly binary to hex. And this is a very useful, quick conversion. So to go from binary to hex, you just start at the right-hand side and break it up into groups of 4. So 1100, which would be a 3, and then 1010, which would be an A, and then 1110, which would be an E. That gives you the hexadecimal. Just by breaking this binary up into groups of 4, starting at the right, you get the hexadecimal. To go to binary to octal, every 3 binaries, not 4, every 3 binary digits is 1 octal. So if you want to go binary to octal, just break it up into 3s. And the same applies in the other direction. If you have, for example, let's move to the next slide here. If I have 1, 2, 3 in base 16, meaning this is a hexadecimal number, 1 is 0, 0, 0, 1, 2 is 0, 0, 1, 0, and 3 is 0, 0, 1, 1. So your binary number is just found by expanding each hex number into 4 bits. And so that's what that would look like, and that's why the quick conversions are very powerful. So this is kind of our summary, but that hexadecimal to binary will come in very useful in your future if you ever deal with microcontroller-based systems. They deal with hex to binary all the time. But doing these in the manual form is useful as well to help understand the numbers. It also directly relates to our project, or our C Applications lab with this topic, because we are going to write our own binary to decimal or decimal to binary converter. So you're going to make a C code version of the conversions that we talked about on the first 2 groupings here, binary to decimal, decimal to binary. One key item to be able to do that is to be able to separate the digits. And so we're going to talk here briefly about division and modulus. You're already familiar with variable types, so you know about integers. They don't have a decimal. So if you do a division with integers, the fractional part is thrown away. So for example, 17 divided by 5. 5 can go into 17 3 whole times, and then the remainder is thrown away. So integer division throws away the decimal, is what's going on in these 3 examples. We have another operator that is specific to integers called modulus, and you use the percent sign for modulus, m modulus n. And that gives you the integer remainder after m is divided by n. So for that 17 modulus 5, remember 5 went in 3 complete times and then had a remainder of 2. So 15 would be 3 complete times, and then there's 2 more unaccounted for. So the remainder of the integer operation is 2. So a modulus gives you a remainder from an integer division. How can we use that to separate digits? Well, let's look at this number as an example. Say this is a decimal number. To isolate the 4th digit, the thousandths place, we can do an integer division by 1,000. So 1,000 goes into that 2 times. 2 even times. The remainder, which would be the decimal part, is lost. Then how do we actually capture that remainder? Is we do a modulus. Alright, and then we can isolate the 3rd digit by dividing by the next lower weight. So that would get us our 5. And then a modulus gets us the 69. So how do we get just 6? Again, divided by 10 gives us just the 6. And then you can modulus to get just the 9. So you now have 2, 5, 6, and 9 all as separate digits just by dividing and then doing modulus, then divide, then do modulus, and keeping track of the number in a variable. Think critically about this slide. This is the process you will have to implement to successfully do your C Applications lab with this topic. I'll discuss it a little bit more in the lead up to the problem video that is coming up in a few pages. But please make sure you follow what I'm saying about separating digits here. This is for a decimal number. You can do the same thing with a binary number in order to separate digits. So just follow along and make sure you understand integer division and then integer modulus and how integers specifically can be used in this technique to separate digits. So our last few slides here just highlighting some other useful number systems. One is binary coded decimal. This is a way to have a direct translation of decimal digits into binary. That means instead of, you remember that 4 binary digits equal a hex. Instead of going all the way up to F, we just cap it at 9. So this is binary coded decimal, meaning we translate the decimal digits directly into 4 bits of binary each. So remember the number 10 you could show as 1010 in regular binary, but for BCD you translate each digit as its own 4 bits. This is a useful number system for things like digital clocks or places where the recipient or intended target is a human user. It just makes it easier to read and separate your numbers. This could be like the clock on the front of a microwave, for example. Another question is, how do we represent alphanumeric numbers, meaning text that you might type on your keyboard, and also the actions like space, backspace, delete? And the answer is the American Standard Code for Information Interchange, or ASCII. So each character is assigned 7 bits that represent that character. And this table is one version here. You can Google image ASCII table and find many versions of this. But this defines what are the parts of that 7 bits total. So here are the lower bits along the top here. These are your lower bits, and your upper bits are on this side. So if you wanted, for example, capital O, which is right there, your lower 4 bits would be F, 1, 1, 1, 1, and your upper 4 bits, we would look over here, are 4. So 4 would be 0, 1, 0, 0. So this is the ASCII number in binary for capital O. In hex, it comes directly from the row and column 4F in hex, or this in binary. So the ASCII table is just a lookup table directly of what binary or hex number represents the characters on our keyboard. So hello, for example, as hex, referencing back to that table, would be this. Lowercase and uppercase are different. So uppercase hex is different from lowercase hex. The numbers are also on the ASCII table. So 0, 1, 2, 3 as characters, and we have a char type of variable that can hold characters. We'll talk more about that later. But those can be represented. So you have to be clear, are you talking about numbers, integers, or doubles, or characters when you consider numbers? And finally, our non-printing characters like backspace, delete, enter, all of those have ASCII equivalents as well. So please be careful when you're considering ASCII versus binary. One is an actual number, one is a code representing a number. So there are a couple last examples here. But an ASCII table is critical for interacting with humans in later applications. So if you're working with electronics in another class later on or out in the workforce, ASCII tables will probably come up as you translate between raw ones and zeros and actual human inputs. The last thing we're mentioning here is this gray code. It's an older machine language. It wouldn't really be implemented in any new installations these days. But just in case you run into it, we're mentioning it. It is set up, the gray code is, so that only 1 bit changes at a time from one row to the next. Only 1 bit changes at a time. And for a machine, that is important, so you're only changing one operation at a time. So maybe this bit controls turning on your motor, this bit controls turning on your brake, this bit controls turning the power on to a second motor, or so forth, right? Bits could represent different physical operations in a factory setting. So gray code is made so only one thing happens at a time rather than switching multiple physical toggles. And you find your gray code by taking the binary and kind of moving through the binary. Start from the left and just duplicate the binary number. When you duplicate it, if the bit to the left is a 1 on the binary, then invert it. So, for example, this 0, just move it over. This 0, just move it over. This 1, just move it over. And this 0, the 0 is moved right there. However, this 1, if we look at the binary, has a 1 to the left of it, so it must be flipped. So it goes from a 0 to a 1. That's why that one changes, because there's a 1 to the left of it right here. And you can follow this pattern on any of these. Copy the 0 over, copy the 1 over. This one has a 1 to the left of it, so it must be flipped from 0 to 1. And this one 0 to 0 because it does not have a 1 to the left. So the sequence is here. That means if you converted the binary of this gray code, it would not count up in decimal 0 to 9 the way that we're used to. But it's structured so that only one bit changes at a time. So that's another side note to remember. ASCII will be far, far, far more common. I will see you in the next video when we discuss our C applications lab. So you will create a binary to decimal or decimal to binary converter program. We also have the midterm exam that you need to complete during this topic. After we do the C applications lab and the midterm, then we'll move back to new topics in C. One note about this midterm is it primarily covers number systems and codes. It's related to the topics we talked about so far. So once you're comfortable with this background information we just discussed, you can take that midterm exam. That'll be one of the 2 tests that we have in this class. And so there are a lot of number systems related questions on this exam. So make sure you're comfortable with this background information. And with that, I will see you in the C applications lab.